So in this video, we're going to be doing the May 23 papers for Analysis and Approaches, paper 2, Timezone 2, higher level. So this is a calculator paper, so have your formula booklet and graphing TI graphing calculator with you. So let's begin. Number one, we have a typical linear regression problem. So it involves the use of bivariate statistics. The calculations here aren't that difficult. All you need to do is just be familiar with your calculator function. So in your calculator functions, there's a case. So the first use you need is to enter in a list. So you need to put in data using the list function on your calculator, or there are tabs like list and spreadsheet. And the next one is a linear regression feature, mx plus b. So it's a simple click of the button. Once you correctly put your data points, so if you have like number of days d, we might put that into list L1. Average height, we might put that into L2, right? So if you input your list correctly, using the linear regression feature is pretty simple. And yeah, so number one, not too many points allocated here. You just need to work your fingers and enter all these numbers. So without even looking at what the question is asking, I know I'm going to have to enter in these values. And by the looks of it, it says the number of days is used to predict the average height. So chances are like the number of days on which so it's like how many days have passed versus what's the height. So obviously we might expect the plants to get taller with each passing day, and we might suggest that there is a linear relationship where height is given by, say, a times d plus b. Okay, so we basically have, if you have a number of days passed, we multiply a certain constant to that and add a certain constant to that. So we would end up with a graph where days and height are linearly correlated, right? So let's move on to our calculator and put in these values. Okay? So you want to go to Stat, List, and Edit. So you will see the tabs for lists L1 and L2. So you want to edit the column values right away. So for L1, I'm going to put in my D. So I'm going to put in 2, 5, 13, 24, 33, 37, and 42. And then I'm going to put in my H values, my Y values, into average height. So I'm going to have 10, 16, 30, 59, 76, 79, and 82. And this is where a lot of fat fingering mistakes happen. So make sure to actually read off the numbers entered into your calculator before moving on, because if you just have a slip of the finger and just write, a wrong digit in one of the 14 digits here, right, you're going to get a completely wrong answer, and then chances are there might not even be, method marks or error carried forward marks. So you want to be very meticulous and accurate when you're doing this. Okay, so make sure to double check the numbers before moving on, right? Because sometimes like you might have numbers all that are like skipped, or you might like have it all shifted down and whatnot. So if that's entered correctly, you want to go to your calculator option again. So exit that to your menu, and you want to go to Stat, Calc, right? And we have the linear regression AX plus B button. So we put in our linear regression AX plus B, and it's going to ask for the X list and the Y list. Okay, so we have linear regression AX plus B, and we're going to say our H is going into our X data, or in our case, our D is going into our X data, right? And our Y is going to be H. So remember that this was L1 and L2. So by default, everyone should have like X list is L1, Y list is L2, and all you have to do is just put enter there, and we get our number. So it says if H is AD plus B, then this A value is going to be 1.93258, so 9326, so that's roughly 1.93. And our B value, it's 7.21662 and whatnot, so we can round that to 7.21. Okay. So we can write that as 7.22, actually. Yep, so the value of A and B will be 7.22 and 1.93. Okay. Next, if we were to use our regression line to estimate the average height of the plants when the experiment has been running for 20 days, what we want to do is we basically want to put in d equals 20. Okay. So the experiment has been running for 20 days, so d is 20. We now calculate what our h is. So we have 1.93 times d, which is 20, plus 7.21. Okay. And we don't want to round prematurely, so we want to kind of write out all these digits. So we're going to do 1.9325874389 times 20, right? Although in writing I kind of truncated it. And then we want to add 7.2166227.905 as far as the calculator shows, even though in writing I just wrote it until 3 sig figs. Okay. So that gives me 45.868 meters, so that would round to roughly 45.9 meters. Okay, so that was only 4 points. In actual test settings, I'm sure you should be able to do it in less than 4 minutes, right? Because you don't even have to think too much about this question. The only thing you need to be worried about is which goes into the x and which goes into the y, and the rest will be done by the calculator. Okay. So number 1 is easily taken care of. Let's go on to number 2. So let's see how many points number 2 is worth. It's worth 6 points. Right? And it seems like we have a triangle and a bunch of shapes, like a real life situation with buildings. Maybe we have like shadows, or we have some cables connecting, right? So we're given this diagram here, so we're likely going to use trigonometry, right? So we will probably use sine, cosine, tangents, and we also have to use, like angle properties. So we might have supplementary angles, complementary angles. We might have like parallel lines, and we might be asked like, what's the relationship between this angle and this angle, right? So be familiar with lines, angles, circles, and triangles, right? So it's just overall geometry. In the first few questions, you'll probably just do those, right? We don't have to go too much in depth into trig functions, right? We don't have to do the sine, cosine functions necessarily, but we will have to use basic trigonometry, and we might use a sine law and cosine law. So if you have unknown angles and unknown side lengths, we know we can use a sine rule or the cosine rule, which is all in your calculator. Okay. So annotating this diagram before moving on, we could say angle APB is going to be phi, right? And we could say like phi is going to be 180 degrees, or pi minus 2 theta, right? So that's like one notation we might say. And let's look for what the question is asking. So the distance from P to A is given as 150, P to B is given as 90. The distance between A and B is given as 154 meters. So let's find the height, h, of the tall building. So in the test setting, you'll probably be able to see the whole diagram in one view, but let me reproduce that diagram from earlier. So these statements are nothing more than, just explaining the annotations. So we had the building here, and we had point P on the ground. So the left one was a higher building. So we had building with the top point A, building with top point B, and the distance from P to B was 90, distance from P to A was 150, and the diagram said these two angles were theta. Okay. And then we want to find the height of the taller building. So we want to find the distance of this origin to A, so we'll call this h. And then we said this side length was 154. Okay, so sometimes the figures aren't directly drawn. They might not even give you anything, but based on the descriptions, you should be able to draw a picture like this from scratch. Okay. So we're going to find h, and from earlier we defined that as phi, where phi is 180 degrees minus 2 theta, right? Or we could say theta is going to be 180 degrees minus phi over 2. So we don't know which will be more, which will come in handy, but I guess we could just find theta first. Or actually, we could just find phi first, right? Because we have triangle APB. So let's say in triangle APB or ABP, we have the SSS condition. So we know the three side lengths. So in the SSS condition or in the SAS condition, which isn't the case, but for future reference. So if we're given the information about three side lengths of a triangle or two side lengths and the angle between, we can use the cosine law or the cosine rule. So basically, it goes like c squared is a squared plus b squared minus 2ab times cosine c. So we have the side length of one of the triangles squared is equal to the side length squared of the other two minus 2 times the side length times cosine c, where the c, so it's important what you decide as side small k c and angle capital C, because we want to make sure that this formula accommodates for the involved like angles and side lengths. So in our case, we probably want to make use of this angle phi, so we want to call this one angle C, right? That would make 154 the side length C, and the other two would be sides A and B. Okay, so this is what we have to fill in. So we would say 154 squared is equal to 150 squared plus 90 squared minus 2 times 150 times 90. And then we would have cosine phi, right? It's perfectly okay to not know what phi is because we can just simplify, right? So if you were to isolate our cosine phi, right, we could go for 154 squared minus 150 squared minus 90 squared, right? And that would leave us with negative 2 times 150 times 90, right? So negative 2 times 150 times 90 times cosine phi is going to be 154 squared minus 150 squared minus 90 squared. Okay, so that's like negative 6,884. So you don't have to write out all the middle values of the calculation, but if you're like me and you're worried about making mistakes and you just want to keep track of your work so that you can like check it later, or so that the examiner can give you some extra points for or like salvation points for like methods, you want to be as detailed as possible. Okay, and then we have 2 times 90 times 150. So that's like 27,000. So we have negative 27,000 times cosine phi is negative 6,884. So that means cosine phi is going to be 6,884 over 27,000. Okay, and you can just write what phi is. Phi is going to be cosine inverse of 6,884 over 27,000. Okay, so let's find that out. So you go to second cosine or arc cosine, right? 6,884 divided by 27,000. And if you get 75, chances are the settings are already in degrees, right? But you just want to make sure that we're doing it in degrees or radians. So it doesn't matter which one you use, but you just have to make sure you're consistent. Okay. So I got my phi as 75.23 degrees. Okay. And then I can find what my theta is by plugging it in here. Right? So that would give me theta is 180 minus this value divided by 2. So that means theta is now going to be 52.385 or 39 or 53 or 52.4 degrees. Okay. So that's what the value of theta is. And then we can turn our attention to triangle AP and maybe O here, right? So we want to look at H. So we know the hypotenuse is 150 in this triangle, right? So I'm just going to highlight this one. So if the hypotenuse is 150 and H is the angle that's opposite to theta, we can relate this with sine, right? So sine theta is simply going to be H over 154. So H is 154 times sine theta. So plugging in my known values, like 154 times sine of 52.39 degrees, right? or so it's written as 52.4, but you can use the stored values on your calculator. And if I convert that into decimals, okay, I get 121.989. So that'd be, oh, it's actually 150, right? So it's 150. So h over 150 is equal to sine theta. So if I multiply 150 here, I would get sine of 52.39 degrees times 150. So that gives me 118.82 meters. Right? And if it doesn't say anything about sig figs, you could round it to 3 sig figs. So I'm going to write 118.82 meters, but you would be fine writing it until 119 meters. Okay. So in this case, just make sure you keep track of all the triangles here, right? There's more than one. Sometimes like one triangle's sharing sides with the other, or there may be some similar or congruent relationships, but as long as you draw a nice, neat diagram in a sufficient scale, and if you like label everything properly, it should be a breeze. Okay. So that brings us to the end of number 2. Let's go on to number 3. So number 3, we have normal distributions with statistics, right? So in statistics, there's like discrete variables, continuous variables, and normal distribution is belonging to like the standard of, to the set of like continuous variables, right? So since we're only in the early stages of the paper, like we won't be expected to do too much. At most, we're going to be using some calculator functions like normal CDF, like the cumulative distribution function, where we're just finding the area under the normal distribution curve, okay? And if it were a question that comes up in the later sections, it might kind of merge with calculus or binomial distributions, and we might have like a whole lot of things going on, but hopefully in number 3, it's gonna stay simple, okay? So as you can see, the questions here are only worth like 2 points each. So yeah, it's like for each question, it's about whether you can nail the proper calculator function or whether you kind of need help with that. Okay. So let's do number A, letter A. So there's a bunch of rice bags that are packaged in a factory. So we know there's going to be countlessly many rice bags that are coming out. And if we measure them, right, sometimes they're going to be heavy, maybe like 220 grams. Sometimes they're going to be 210 grams, maybe 25 grams, or sometimes you might have a very light bag of like 195 grams. So it's going to be variable, right? But if we were to keep track of that, it would probably be a normal distribution curve. So the weights are going to be centered around a certain value, and then there are going to be some high-end extremes and low-end extremes. So it says the mean is going to be 204 grams, right? And the standard deviation is 205. The standard deviation is 5 grams, so the spread is like 5 grams. So on average, so we don't need to know like the exact definition of the standard deviation here. We just need to know what to put into our calculator function. Okay? So some bags are heavier, some bags are lighter than 50. 204, so it's like a 50% mark here because the normal distribution is symmetric. But part A is asking, if you were to select a bag at random, what's the probability that it falls into this region where it's greater than 210, right? So W is a normal distribution, right? So W is a variable, right? The weight of bags that follows a normal distribution with mean 204 and standard deviation like 5 or variance 25. And we want to find the probability where W is greater than 210. Right? So this is the formal notation that we write, and we would put that into our calculator. Okay. So we can go to second distributions, and we want to open up the normal CDF function, because the normal CDF function allows us to take for a certain defined normal distribution, like with a certain mean and a certain standard deviation, right? So for a mean of 204 and standard deviation of 5, what's the area between the lower bound and the upper bound, right? So that's what the norm CDF does. And in our case, the lower bound is going to be 210. And the upper bound is going to be limitless, right? It's going to be infinity. So if you know where the infinity button is, you can put that. Or we could write an arbitrarily large number, maybe like 1 million. Because 1 million is going to be like way down the road here. So yeah, we can just write a sufficiently large number. Doesn't make a difference. Okay, and we want to enter our mean and standard deviation. Right? So this is for our specific distribution. If you had different means and standard deviations, it would be a whole new curve, right? It would be a whole new bell curve. So if you put that, the probability turns out to be 0.115. So there you have it, right? Like 11.5% of bags are on the heavier end, right? So if you were to randomly draw a bag and it weighs more than 210 grams, it means you got like the top 10% or top 11.5% of the results. Okay, next. For this model, it says that 80% of the bags weigh between W grams and 210 grams. So we want to find the probability that our weight is less than this small w. So don't get confused. Like the capital W is a variable. The small w is like it's like a constant that sets like the boundary or threshold value. So we draw the same normal curve, and W is likely going to be on the lower end. So 80% of bags of rice will fall in between this region. Right, so we already know that greater than 210, that's just going to be 11.5%. Right? So if the area between W and 210 is 80%, we know this has got to be 8.5%, right? So we just got to subtract, right? So this would just be 1 minus 80, or 0.8, minus probability that W is greater than 210. Okay, so if you do that, 1 minus 0.8 minus the stored value here, we would get 0.0849. So 8.5% is a chance that the rice weighs less than W grams. Okay, then let's find the value of W. Okay, so from earlier we said W is here. This would be 0.0849. So if you were to use normal CDF, we know what the area under the curve is for a given boundary. But in this case, we're doing the opposite. We're doing the inverse of that, right? Because we're given the area and we're trying to find the boundary. So in that case, we're actually using the normal distribution, inverse normal function. So if you have inverse norm, so it's found at the same menu alongside like second variables distribution. So right below normal CDF, you should find the inverse norm feature. So that allows you to put in the area and the mean and the standard deviation. So as earlier, right, same as earlier, the mean is still 204, the standard deviation is 5, and what we put into the area is the lower end, or the left tail area, right? So in our case, it would be 0.0849. So for the lower tail end of the area, which is like 0.0849, we know the boundary value is going to be W, right? So that's what the normal, inverse normal returns. Right, so what value would W have to be in order for the probability below that to be 0.0849 is what we're asking our calculator. Okay. So if we enter that correctly, we should get 197.136, or around 197.14, or roughly like 197 grams. So I think this makes sense, because if our center is at 204, and if W is 197, then we're roughly like 2 standard deviations below. So that's going to be like on the lower extreme. Okay, so you can also check this using norm CDF, right? So you can check with norm CDF. So you could do this on your own time, like not necessarily during an exam, but if you were to go to second variables, norm CDF, and if you were to put in the lower bound is like negative infinity, or a negative large number, and if the upper bound is like 197.135, and if the mean is 204, standard deviation is 5, then this should give you like 8.5%, right? And we see that is true, so Norm CDF and inverse norm, they should be dealing with the same normal distribution, so you can kind of use one another to like check for each, right? Check whether the solution is correct. Okay, so that's how you would do C, and now on to D. So we have 10 bags of rice that are selected at random. So this is what I actually mentioned earlier. Usually they do this for like the later questions, but they often, what the IB likes to do is they like to tie in normal distributions with binomial distributions, right? Because we know that for a single bag of rice, we know that we have to measure its weight. So it could be like anywhere along this normal spectrum, right? But we just identify two cases, right? It could be that the measured weight is greater than W or the measured weight is less than W. So the probability that one bag weighs less than W grams, we said that was 0.085 or 0.0849, right? And the probability that the bag exceeds that is going to be the complement of that. So 0.910 or 9151, right? So for a single bag of rice, it's just two cases, right? It's like 91%, 8%, right? But we actually have 10 bags of rice, and what we're doing is each of these bags of rice are identical, and we're actually counting how many of them weigh less than W grams. So that's the definition of a binomial distribution. So you might say, let's say like B is the number of bags of rice weighing less than W grams, right? In this case, 197 grams. Then the values of B would be anywhere between 0, 1, 2, 3, all the way to 10, right? Because we have 10 bags total, we could have 0 bags all the way to 10 bags that are weighing less than W grams, right? So in that case, we would say B actually follows a binomial distribution, where the N, the number of trials, is going to be 10, and the probability of success is going to be 0.0849. Okay, so that means this binomial distribution can find the respective probability that B will be either 0 all the way to 10. Okay, so in this case, we're actually looking for one of the bags to be less than W grams, right? So what we would do is for this particular variable B, we're going to use binom PDF. Okay, so if you go to binom PDF in second distributions or variables, you can go like straight down. You'll see the collection of functions like binom PDF, CDF, Poisson PDF, CDF, and geometric PDF, CDF. So in this case, you want to go to binom PDF. So it gives you the probability that our variable will take a certain value. Okay, so for a binomial distribution where the number of trials is 10 and the probability of success is 0.0849, we're going to ask what's the chance that our x is going to be 1, right? So where we're going to observe like one value, right? One instance of success. So 1 will be lighter, 9 will be heavier than W grams. Right, so we put in 1, and the probability turns out to be 0.382, which is 38.2%. Okay. So if you have 10 bags, like 38% of the time, around one of them will be light and 9 will be heavier, right? So it seems like a pretty large probability, but it makes sense, right? Because out of every 100 bags, we know 8.5 bags are lighter. So in 10 bags, right, I guess the most likely value is going to be 1 bag out of 10. Right? If you want to see like 5 bags being lighter, that would represent an anomaly. So this is how you would do it using the calculator, or you could do it manually, because in one bag, you're going to observe a case where it's light. So there's a 8.5% probability where one of the bags is light, and there's a 0.915 probability where the bag is heavier than W, but that should happen 9 times. But we don't stop there, because there are 10 bags total, and we have to decide which out of the 10 bags is this rice bag going to be light, and which 9 of the 10 will be heavy, right? So we have to multiply 10, choose 1. So you could do exactly that. So you could go to math, you could go to probability, NCR. So we have 10, choose 1 times 0.849 times 0.91 or 951 to the power of 9. And that would give you, oh, it's 0.0849 by the way. Right, and that would give you the same result. Oh, and it's also 0.915, not 951. So careful of the typos. Yeah, so you should still get 0.382, whichever way you do it. So if you have a reasonable understanding of binomials, then you could set up this relationship yourself. But if it's kind of fuzzy, you can always use your binom PDF function on your calculator. Okay. So that was like a surface level problem for normal distribution. Like I know questions could get a heck of a lot deeper than that. Okay. So now let's move on to number 4. We have binomial theorem and combinatorics. Yeah, it's the same word of binomial, meaning there's like two. So bi means like two, right? Like bicycle. So binomial distribution is like a case where there's like two probabilities. Binomial theorem is basically if you have a binomial term like this and we're expanding it by raising it to the power of a certain integer, right? So this is like one of the earliest things you did in junior year. So in the first year of IB, you probably did this with numbers and algebra. So this is all about using the formula correctly, the binomial expansion formula. And this one is worth 7 points. Might seem a bit high because there's a lot of variables. So chances are you're going to have to use the binomial theorem formula to find relationships between these unknown variables, and then you're going to have to solve for them, you know, using systems of equations or using substitution. Right? And then we see that there's a connection with sequences because it says like the coefficients here are first 3 terms of a geometric sequence. Okay? So we're basically using sequences, binomial theorem, and 1. So it's like a multi-package problem. So let's first write the relationships. So coefficients A, B, and D are first 3 terms of a geometric sequence. So a geometric sequence is when there's a common ratio R. Right, so we can multiply like R to the preceding terms. So if you have like U1, U2, and U3, we can multiply R to U1, and we can multiply R to U2 to get the next term, right, like U3. So A times R is going to be B, and B times R is going to be D, right, for some common ratio. You could do that, or we could say the common ratio is found by R, which is B over A, which is equal to D over B, right? So that's one way you could use this hint, right? These 3 coefficients are 3 consecutive terms, right? The first 3 terms of a geometric sequence. So that's how you would relate A, B, and D. And then we can look at the first part. So after that's done, we can say we have x to the power of 8 plus ax to the power of 7, right? So we would get 9 terms where the powers of x is decreasing and the powers of h is increasing. And h is also a constant, okay? So let's find how we would get a times x to the power of 7. So this is found by, so if we have like x plus h to the power of 8, we know we would get a total of 9 terms. So for confusion, I'm just going to erase this whole concept of R. So all we need to know is that from earlier, we can just say B over A is a common ratio, which is equal to D over B, right? Because R is used in this formula as well. And then if you have x plus h to the power of 8, then R goes from 0 all the way to 8. And then we have x to the power of 8 minus r, and then we have h to the power of r, and then we have 8 choose r, right? So this is the formula we know. So r can take any one of the 9 values from 0, 1, 2, 3, 4, 5, 6, 7 to 8, right? And it would give you all of these matching terms, right? So if you want to find the first case, like ax to the power of 7, What would r have to be? Well, r would have to be 1, right? Because if r is 1, then we get the term where we have x to the power of 7, and then h, right? And then we get h choose 1. So if r is 1, we get our value for a. Okay, next, we get our value for b, right? So we want b x to the power of 6. So r would have to be 2 in this case. So we would get 8 choose 2 x to the power of 6 times h squared. That's going to be b times x to the power of 6. The third case, we want c. Okay. So c x to the power of 5 is going to be when r is 3. So 8 choose 3, x to the power of 5, h to the power of 3. Right? So this happens when r is 3. And then lastly, we can also do when r is 4. Right? So if r is 4, we could say that, so if r is 4, the fourth piece of info is that we have 8 choose 4, x to the power of 4, h to the power of 4, and then we get dx to the power of 4. Okay, so I know there's like 5 bits of info here, because we'll call this like piece number 5. So there's like 5 exclusive hints. B over a is equal to d over b. So we could say something like b squared is equal to ad, right? So that's like one piece of info we can use. And then we can try and simplify the other ones here, right? So the end goal is to look for h. So we might have to find a, b, c, and d, but if you don't have to, right, you could just leave it as blank, because the end goal is to find h, not the other ones, right? So we will probably find the other ones as well, but try to look for a simpler way if you can. Okay, so if you look at number 1, 8 choose 1 is going to be 8, right? So you can just check with 8 choose 1, because there's 8 ways to choose 1 out of 8. Yeah, so 8 times x to the 7 is going to be multiplied to h, and that's going to give you a, right? So the next piece of info is going to be 8h is going to be a. Right, so from piece 1, we know that 8h is going to be a. From piece 2, 8 choose 2 times x to the 6 times h squared is going to be b. So if you do 8 choose 2, oops. So if you write 8 choose 2, that's going to be 28. So we know 28 times h squared is going to be b, right? We're not going to bother writing the x to the power of 6. Next, we have 8 choose 3 times x to the power of 5 times h to the power of 3 is equal to 6 c x to the power of 5. So we could do 8 choose 3. Right? So we have 8 choose 3. And then that's 56. So it's like 56 times h to the power of 3. That's going to be equal to c, right? Okay, so we have 56h3, h to the power of 3 is equal to c, right? And then the last piece, 8 choose 4 times h to the power of 4, that should be equal to d. So if you do 8 choose 4, that's going to be somewhere like this 70. So 70 times h to the power of 4 is going to equal d. So we have 5 equations and 5 variables like a, b, c, d, and h. So let's try to solve for this. The good news is we probably don't have to figure out what c is, because it's kind of standing on its own. Right? So it's like an extraneous piece of info. And then we can try to relate the other ones, right? Like we have the relationships like b squared is ad. So we could try doing b squared and multiply a and d together. So let me write b squared is going to be ad. So 28 h squared is going to be 8h times d, which was 70. h to the power of 4. Okay. So if you do that, 28 squared is going to be 784. H to the power of 4, that's going to equal 560 h to the power of 5. So if we were to divide the h to the power of 4 on both sides, you get h on the right, and on the left we would get 784 divided by 560. That would be 7 over 5, or 1.4. So actually we just found h right away. I kind of wrote all the 5 pieces of info so that you could follow along, but in the actual test setting, you probably won't have to do all of it, right? Maybe you could find like 2 or 3 pieces of info and try to get working on the solution. So yeah, it shouldn't take you that long. It's only 7 points, so the ideal target for solving this is 7 minutes. But yeah, I'm sure there are multiple avenues to approach this. I just showed you all the info that you could work with. Okay, so that's how you would do number 4. As long as you're familiar with the binomial theorem formulas, you should be good to go. So now let's move on to number 5, right? So we have a kinematics problem. So we have velocity given as a function of time. So it's a function like v of t, right? And we have a bit of exponential and we have a bit of cosine here. Okay. And do note that we usually deal with functions in the form of like f of x, but in this case we have v of t. So t goes on the x-axis, v goes on the y-axis, right? So just make sure you're familiar with the notation. And time goes from 0 to 4 pi, but this is obviously in radians. So we only use degrees when it's like explicitly an angle, but when a variable is a input going into a sine or cosine or tangent, like a trigonometric function, then the units would be radians by default. Okay, so let's just enter this into our graph for now. So let's just enter this expression. Instead of v, I'm going to write y1, and instead of t, I'm going to write x. So we have 4 e to the power of negative x over 3 times cosine of x over 2 minus pi over 4. Okay, and usually the calculator is smart enough, and minus. So usually the calculator is smart enough to like use a correct order of operations, but I like to use brackets to keep track of the order of operations, like brackets, multiplying, dividing, because it's not really about the calculator, it's about you, right? Because sometimes you might input an expression into the calculator and you might put it in such a way that you're evaluating the wrong expression. So I'm just going to write what I put in my calculator because this is going to be used again and again. Okay, so the expression that you want to put into your calculator is for y1, you want to write 4 times, so you would press the multiply button, then we have e to the power of, right, or exponential to the power of negative x over 3. And this negative sign would be like the negative sign, not the minus, right? It's different. And then I would write a multiply sign again with cosine, and then I would put in brackets, right? And then we have x over 2 minus pi over 4. But I would add another bracket to have x over 2, so that this is always evaluated first, minus pi over 4. Right? So you can find the value. So don't just write 3.14. There is a button for pi. You just have to click second exponent. Right? And then I'm going to close my bracket. Okay. So this should be the expression that you should have, right? And I would recommend using these brackets because if you miss a bracket, you never know like how the calculator might interpret it, right? So if you just write e to the power of negative x over 3, right? Like maybe you could have made a unsubtle mistake such that we have e to the power of negative x over 3, or we have like e to the power of negative x over 3, and then we might have like cosine going on the top. So I would try to keep track of everything with sufficient parentheses, right? So the calculator will always evaluate expressions in the parentheses first, and then I would change my settings to radians because we're not dealing with degrees. So number one, check that you have the correct expression. Number two, make sure it's in radians, not degrees. So there are cases where we might have degrees, but in this case, it's radians. And then the window settings, right? If you look at the problem here, it goes from 0 to 4 pi. So 4 pi is roughly 12.56, right? 3.14 times 4. So we want to set our windows such that x goes from maybe like 13 from 0, right? And I want to start from maybe like -1 because I want to see the details beyond that, beyond the origin. And then you could graph it first and then later adjust the y. But the y value, right, I think if you just do from -2 to 4, you should be able to see all the details that you need. Right, so if you get the scales right, that should produce pretty much the exact same graph that you see on the calculator. So on my calculator, I get a graph that looks like this. So 4 pi would be somewhere here, like 12 point something. But we know that there's like 2 zeros where it goes from, where v goes from positive to negative and then negative to positive, right? And although the question starts off at like 0, we know that it kind of goes down at the negative region. So that's the advantage of copying and pasting this expression into your calculator. You can kind of see the full expression that the question doesn't give you the details to. Okay. So what do you need to find? T1. Okay. So T1 is the first time of the particle's acceleration is 0. So note that acceleration as a function of time is basically v prime t. So v prime t going to 0 means, in the case of our v to t function, we're looking for the stationary points. Basically when the tangent line has a slope of 0. So we see one point, that's like here, that's going to be T1, because the tangent line is going to be straight up vertical, T1. And then there's going to be another one, T2 here. Or actually, this isn't T2, it would just be another point where the acceleration is 0. Okay, so I'm gonna find the maximum point, right? So the max point, so the local max or minimum of Vt is going to be when v prime t is 0 or when the acceleration is 0. Right, so the velocity is increasing, then it peaks and it's about to stop. So yeah, that would be the case when acceleration is 0. So I go to second trace and I'll choose maximum. So I find the local maximum between x is 0. That's my left bound. And my right bound, I could put in anything, but I don't want to go past like 6 because we have a local minimum here. So yeah, we don't want to like put in too wide of a range. So we definitely know that our maximum is between 0 and 2, right? Because our maximum is between 0 and 2 here. So that's what I'm going to put into my calculator. Right? So my right bound is going to be 2. So it correctly gives me 0.39479. So T1 is going to be 0.395 seconds. Right? So on your calculator, it should return this point as 0.395 and 2.92. So at 0.395 seconds, the velocity is 2.92 meters per second. The acceleration is 0. Next, the particle is at rest at T2 for the second time. So we want to look for when Vt is going to be 0, right? So we see the first one right here. That's when the velocity is 0 momentarily, right? Because it's going in the positive direction and it's just about to change to the negative direction. And it goes in the negative direction and then it changes to the positive direction. So this would be the second time where it's instantaneously at rest. So this would be T2. Okay. So we have V of T2 equals 0, right? So we would just look for the local 0, right? So we go to second trace, 0. And the calculator can find you the 0 of the function easily as long as you specify the boundary in which the 0 is located. So the 0 is obviously greater than, say, like 5. I'm going to put that in my left bound. My right bound, I'm going to say something like 12. So that should net me the T2 value. And it is 10.996 seconds. So the coordinate is like 10.996-ish and 0. So T2 is going to be 11.0 seconds, rounded to 3 sig figs. Okay. Now, I want to find the distance traveled between these two times. So you might think it's just integrating from 0.395 seconds to 11.9 seconds. Not as simple as that, integrating from like distance, right? Or let me just write the expression for distance. So you might think it's just a matter of writing this expression, like x over 3, or actually t over 3, and then cosine t over 2 minus pi over 4 dt. So x and t are interchangeable. In your calculator, you would probably use like x instead of t. But then the catch is there are regions where the displacement is positive and regions where the displacement is negative, right? So if you were to do this one, it would actually get you the displacement where if you move to the right and come back, then, if you move like 5 meters right, 3 meters back, then the displacement is going to be 2 meters because we have negative and positive. So what we want to do is we want to put a absolute value sign here, because this will show that regardless of what the displacement is, we're always going to be adding, right? So that's as simple as it gets. We can just find the absolute value function of that. So what we could do is we could perhaps copy this full thing. So you can copy the full expression from your calculator. Okay, so let me just select. And if you go to math, numbers, you can choose the absolute value sign. And then you could paste the values. Yep. So you could just graph the function where there's a absolute value sign involved, right? So that means you'd get a VT function where it's the same thing in the positive region, but where we were supposed to have a negative region, it's also flipped so that we get a positive region. So this one is flipped, and then it kind of carries on. So now we're going to find the area bound by this curve. So we're going to have positive, positive, positive areas. So let's go to second trace, and let's go to the last option, which is the integral sign. So we're going to find the integral from 3.95 or 0.395. Right, so that's our left bound. Our right bound is 11.0. So if you find the area under that, it should give you somewhere along the lines of 7.83 meters. Yeah, so evaluating that expression is 7.83 meters. So always important to know the difference between distance and displacement and when to use the absolute value sign. Okay, so you could do that on your calculator in the graph mode, or you could go to math, FN integral, and there's a way where you can just input the whole expression again. So 0.395, 11.0, and then I would put in my absolute value sign, and then I would write in 4 times e to the power of negative x over 3 times cosine of brackets x over 2 minus pi over 4, close brackets, right? And I would tell the calculator to evaluate this right away. And it should give me the same result of around 7.83, right? So there you have it. Number 5, we have 7.83 meters. So now let's do number 6. We have vectors, intersections, and planes. So I think this is one of the harder topics in the IB/HL papers, because sure, we know like how to apply dot product, cross products, but when it comes to the questions, you kind of have to be able to have a intuitive understanding of what's going on, and you need to be able to infer the meanings of like what it means if the two planes are intersecting and there's a line, or if there's like a normal vector to a plane, like what is that, right? Or if we're trying to find the shortest distance, how can you use orthogonal or perpendicular vectors? So there's like more than meets the eye in these vector questions, because you see these expressions for lines, planes, and whatnot, but you have to know what's going on, and that's kind of happening in behind the scenes. So you need a lot of like practice, and you need to be exposed to different kinds of problems with vectors. And yeah, like my strategy is, if there's a question where you kind of can't really get started on this vector, like it's perfectly fine to just go hit another question and try and come back, right? But let's try to do number 6 the correct way. Okay. So we have two planes. Pi 1 is 2x minus y plus 2z is 6, and pi 2 is 4x plus 3y minus z is 2. So we know that 2 minus 1, 2 is a normal vector. So pi 1 is going to have a vector going in a certain direction like this, right? 2 minus 1 and 2. That is going to be perpendicular to the entire plane, right? And then we have normal vector 4, 3, minus 1. So we're going to have another vector, another plane whose normal vector is heading in this direction, right? So the details aren't really important right now. It's more about the concept you get, right? Because what we have here is that there's a line of intersection between pi 1 and pi 2. So what that looks like is we're going to have like a plane that's going this way. So we'll call that pi 1. And let's say we have another plane going in this way as pi 2. So that means this could be the intersection of line L. So line L belongs to plane pi 1, but it also belongs to plane pi 2. Okay. So that's interesting, because that means whatever the value of L is, right, it's saying that the xyz is given as lambda minus 2 lambda plus 2 minus 2 lambda plus 4, right? So for a certain given value of lambda, this is what the xyz is. But for any value of lambda, so for any point on line L, it should work, it should satisfy the expression for planes pi 1 and pi 2. So basically, we want to substitute this into this expression as well as this expression to confirm it all makes sense. So we might write if L is on plane pi 1, right, we might say 2 times the coordinates of x, in this case, which is lambda, minus y, which is minus 2 lambda plus 2, plus 2z, where z is minus 2 lambda plus 4, equal to 6. Right? This should make sense. And reorganizing that, I'm going to write 2 lambda plus 2 lambda minus 2 minus 4 lambda plus 8 equals 6. Right, so this should hold true. And does it hold true? Yeah, because if you organize everything, we get the left side as 6 and the right side as 6. Right? So of course, if you were to do it formally, we would have to start with, this is my left-hand side, this is my right-hand side. So if I manipulate and algebraically evaluate this, I end up with a 6, which is indeed equal to my right-hand side, right? So basically, we just want to confirm that x equals lambda, y equals minus 2 lambda plus 2, z equals minus 2 lambda plus 4, right? That satisfies the expression for plane pi 1. And then I want to do the same for pi 2. So if line L is on plane pi 2, what I'm going to do is I have 4 times x, which is 4 times lambda, plus 3 times y. That would be 2 minus 2 lambda, minus z, which is 4 minus 2 lambda. So this is going to be my left-hand side, right, which is going to give me like 4 lambda plus 6 minus 6 lambda minus 4 plus 2 lambda. That would evaluate to, so the lambdas would go away and I would just get 2. Okay. So just to reiterate here, so for more space. Right, so if I evaluate this expression, it gives me just 2, which is indeed equal to the right-hand side. So basically, whatever value of L we have for whatever parameter value of lambda, the specific XYZ coordinate also works and satisfies the equation for the plane pi2. Okay, so that's how we know that this vector equation of L, right, is indeed belonging to both planes, right, pi1 and pi2. So you just need to show that. It's like a mini proof exercise. And then let's go on to number 2, or part B. So we have coordinates on P, which are on line L, and we want to make sure that it's closest to the origin. So let's say we have our line L. So let's not think about the planes right now. Let's just think about how L is like lambda 2 minus lambda, or 2 minus 2 lambda, and 4 minus 2 lambda, right? So for whatever value of lambda we have, we get a bunch of XYZs that represent line L. And let's also have a origin, right? So if you have like the X, Y, and Z axis, however that may be, we have our origin here. Okay. So if our line L was moving, right? So there's no guarantee that it's moving through the origin, right? So we may have different instances of points on line L, and we can measure the distance d each time. So d would represent the distance between the origin and a random point on line L, right? So a random point meaning for a random value of lambda. So we want to find the minimum value of d, right? So there are 2 ways that you could do this. One is just set up an equation for d and try to minimize that. So the first approach is we use d as a function of lambda, right? So if you want to find the distance between 2 points, we do x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, right? So the formula for distance between 2 coordinates like x1, y1, z1, and x2, y2, z2 is something like that. So you should be able to find this formula in your formula booklet. So you could say that we have 0, 0, 0. So that's going to be x2, y2, z2. And x1, y1, z1 is going to be like lambda, 2 minus lambda, and 4 minus lambda. So we're just going to do lambda squared plus 2 minus 2 lambda squared plus 4 minus 2 lambda squared. So if we evaluate this expression, that's going to be the distance, and we want to, okay, so let's first simplify that. So d would then be square root of lambda squared plus 4 minus 8 lambda plus 4 lambda squared plus 16 minus 16 lambda plus 4 lambda squared. So d would be square root of 9 lambda squared, and then we would get negative 24 lambda plus 20. So what we want to do is we want to do like dd over d lambda is 0. So lambda changes and it affects d. So if you find dd over d lambda, so the rate of change of d with respect to lambda, that means d would be either a maximum or minimum point, or you could just graph this onto your calculator. So for a certain value of lambda, that's going to decide our point on L, right? And that's going to give me the distance d. So I could just find the minimum value straight off. So that's like approach 1. And the other approach involves a intimate understanding of vector. So we'll get to that soon, but let's just check the results. So if you have 9 lambda squared, instead of lambda, I'm going to do x squared minus 24x. And then I have plus 20. Okay. So if I plot that, so lambda could be any values. I'm going to write from maybe negative 10 to 10. or maybe like -5 to 5. We'll zoom out if it's necessary. Okay, and if you zoom out, there is a minimum value there. So let's find the minimum value. So the minimum is going to be between 0 and 2, clearly. So we have lambda is 1.33. So it turns out if lambda is 4/3, then the d is minimized. So what you could do is just plug in lambda is 4/3 into this expression for L. So we would get 4/3, 2 minus 2 times 4/3, so that's going to be -2/3. And then 4 minus 2 times 4/3, that's going to be 4/3. So this would be sufficient to get you all 5 marks in this answer, right? Because this is the graph we got, and this is 4/3. But there's a second way to do it, which is using vectors. Okay? So if we have point P on L, and we have the origin, right? What we could do is if we were to draw a line OP, so this is our second approach, the direction vector of OP is going to be perpendicular to the direction of L, right? So OP is going to be perpendicular to the direction vector of L. The direction vector of L was going to be 1 minus 2 minus 2, right? So this was the direction vector of L, right? Because that's like the closest way we could go. Right? For any other point, we see that it's not perpendicular, but when this is perpendicular, we see that we have the shortest distance. So that just means if we were to take the dot product of the direction vector of L, which is 1, -2, -2, with the direction vector of OP, right, that would have to be equal to 0. Now, how do we find the direction vector of OP? We subtract the coordinate of P from 0, 0, 0. So the coordinate of P is actually lambda 2 minus 2 lambda, 4 minus 2 lambda. So we get lambda 2 minus 2 lambda, 4 minus 2 lambda. So if you take the dot product of that and solve for whatever lambda should be, we should get the same. Lambda is 4/3. So there are 2 separate ways in which you could solve this problem, and it kind of depends on which fits your style more. Like I would personally say the second method works better because you just have like a straightforward relationship to finding lambda, and you don't necessarily have to use a calculator. But if you find that a bit confusing, or if you just if you fail to see that relationship, the whole like perpendicular directions, then you'd be perfectly fine just doing the minimizing d with respect to lambda. Okay, so both methods work. There are many ways you can get full points in IB. So that was definitely more on the challenging end of the scale. So if that was a bit confusing, don't worry. Like you could definitely just like leave that, skip it, and come back to it later. Okay, so now let's do number 7. We have a typical calculus problem with functions, and we have solids of revolution. So if you have solids of revolution, you can just pop up to your formula booklet and see what the question's wanting. Okay, but the cautionary note is you always need to measure or like read out where it's being rotated, right? Because we might assume it's always being rotated about the x-axis, but when it's being rotated about the y-axis, it's a whole different expression. Okay, so before even doing that, I would just plot out what my f of x would look like. So if I have my x and y, I would draw arc tangent x minus 2. So I know that my arc tangent function would look like that, but since we have minus 2 inside, we know the whole thing is shifted to the right. So we would get a graph that probably looks like that somehow. And then x is going to be greater than 2. Okay, so if x is 2, f of 2 would be 0. So we know there's like a 2, 0. And it goes up until 2 plus root 3. Okay, so if this is 2, this would be like 2 plus root 3. So for a typical arc tangent, if we were to have root 3, it would give us like 60 degrees, right? Or pi over 3. But since the whole thing is shifted, right? If you put in x equals 2 plus root 3, that's going to be pi over 3. So this point, right, is going to be y equals pi over 3. Right? Because if you put in x equals 2 plus root 3 there, we get arc tangent of root 3, which is pi over 3. Okay, so you could do this mentally inside your head, or you could just plot this out right away, because you can just plot arctangent of x minus 2, and make sure we're dealing with radians, not degrees, and we want to make sure that our our window is correctly set, maybe from like x equals 1, or actually we'll just see from the negative, like x equals minus 2 to 2 plus root 3, that's like no more than 5. Yep. So our graph would look something like that. Yeah, so it does go on a bit in the negative direction as well, but all we need to know is this part. Okay. And what are we doing to this? The region bounded by this curve, the y-axis, the x-axis, and the line y equals pi over 3. Okay, so that's pretty convenient for us because when y is pi over 3, x is 2 plus root 3. So the function is only defined until that point. So this is the area that's bounded. Okay, now we want to find the volume of the solid if it's rotated about the y-axis. So you got to be careful because you can't just use a v equals pi integrate like f of x, right? Because that's only for rotating about the x-axis. Since we're rotating about the y-axis, we would have to do like, we would have a radius as x, or f of inverse of y. So we'd have f of inverse of y squared dy, right, for some minuscule thickness, dy here. And then we would go from y equals 0 to y equals pi over 3. So we have the boundaries for the y value. Okay, so this is the expression that you have to evaluate. Okay, so that would give you the volume. And so let's find f inverse. So if you have y is arctangent of x minus 2, to find the inverse, right, to find f inverse y, we want to switch the x and y, right? So how would you represent x in terms of y? Let's just put tangent on both sides. So then tangent y would be x minus 2. So x would be tangent y plus 2, right? Pretty simple. You can just do this equals pi, integrate from 0 to pi over 3. And then we would do tangent y plus 2 squared dy. So evaluating that should give you the volume. So 5 points might not seem like much, but if you were to, say, revolve it about the x-axis, right, that would be a pretty harsh case because you would still do the work and not get full points, right? Because you just found the volume of the wrong solid. So let's go to integrate from 0 to pi over 3. So we have pi over 3. And then we have tangent y plus 2 squared. And then we multiply pi to the whole thing. So that would give you like 24.02 or roughly 24.0. Okay, so that's how you would do number 7. All right, so now we have number 8. It's a typical like range and domains functions problem. So it doesn't look that hard on the surface because like what worries us is usually if there's like vectors or calculus, but on the surface it seems like a pretty straightforward question. But this is actually where a lot of students might lose a point here and there, because the function itself is pretty like complicated. If you have like rational functions or if you're multiplying like cosine to this function, and we have like absolute value signs applied, right? And this is applied inside the brackets, right? Inside the input. So we kind of need to be aware of those and navigate through those relationships and traps. So I would rate this one pretty high on the scale of difficulties. So first, let's do g of x. So let's plot g of x and find the range. Okay. So from the get-go, we know that there is going to be a horizontal asymptote because the degree is greater in the denominator than the numerator, right? So we have 2x minus 5, divide that whole thing by x squared minus 3. Okay, and x can't be plus or minus root 3. That's understandable because that would mean the denominator is going to be 0. So we go to infinity. So I would write x cannot be root 3, and x cannot be negative root 3. And no. Not surprisingly, our calculator kind of supports that idea because we seem to be able to capture the details of the vertical asymptotes in our calculator as well. Okay, so if you were to plot that, yeah, we get the full shape with the horizontal and vertical asymptotes. So the vertical asymptotes are here. If you look at the central region, we see that there's like a graph that has a y-intercept that's slightly below 2, and it seems to have a minimum point on the positive first quadrant side, where it then hits the minimum point and then goes above. So this minimum point, this local minimum point, is of our interest. On the left, it's so as x goes to negative infinity, right, we see that the denominator would be far greater. It would outpace the growth of the numerator, so you would go to y equals 0. And if we go to negative root 3 from the lower end, we see that we get a negative infinity number. So this is what happens here. Right, so that's what we get here. And then on the right side, we have the vertical axis, or vertical asymptote. We have the x-intercept at somewhere greater than 2. And then it's kind of hard to see the details, but you might think it goes like that. So we start from the vertical asymptote, and you might think it's just an increasing function. But actually, what we know is if x goes to infinity, then y has to go to 0. So we would actually have a horizontal asymptote at y equals 0. So it's actually possible for our graph to go cross this horizontal asymptote and then approach this y equals 0 as we keep going. Right? So vertical asymptotes cannot be crossed, but horizontal asymptotes can. Okay, so that means we actually have a maximum point. And this isn't drawn to correct scale, but yeah, the maximum point will be somewhere around here. Okay. So if you want to find the range of g, we would find the local minimum point and the local maximum point, right? Because greater than the local maximum, local minimum, and less than the local maximum, right? So greater than the local minimum and less than the local maximum is our effective range. So let's find the local minimum first. So the local minimum turns out to be 0.697 and 1.43. So g of x must be greater than or equal to 1.43, or we can find the local maximum point here. So left bound I'm going to say is like 2, right bound I'm going to say is like 4, so it's like, or actually the local maximum is going to be somewhere around 4.30. So actually, yeah, this one is greater than 4. So it's like from 4 to 5, we have 4.30 and 0.232. Okay, so we have g of x is less than or equal to 0.232. So this would be the range of g. And I would say it's pretty important to kind of sketch this clearly without any, so if you draw it in a very small graph space, then you're going to kind of like mix these details. So I would recommend that you have enough ample space to represent all these details, because this will help you up, help set you up for success in the next problem. So the next one says we have a new function h of x, where it's basically cosine of t multiplied by g of absolute value of x. Okay. And cosine t. So t, thankfully, isn't a variable. It's just a constant that's between pi over 2 and pi. So it's in the second quadrant. So we want to look for when h of x is less than or equal to 0. So if you do like g of x absolute value times cosine t is less than or equal to 0. Let's first think about what cosine t does. So remember that unit circle? We have like all students take calculus, all ASTC. So the cosine value is positive in the first and second quadrant. But what we have here is, first and, so this is the first quadrant and a fourth quadrant, right? But in the second quadrant, the sign is only positive, so cosine is negative. So if you have an angle t, it would be in the second quadrant like that. So the cosine of t would definitely be less than 0. Okay, so we would make a note that for t in between pi over 2 and pi, cosine t is less than 0. Okay, so cosine t is less than 0. So that means g of absolute value of x is greater than or equal to 0. Okay, now let's think about what g of absolute value of x is. So if you think g of absolute value of x is simply flipping this one to the positive side, that's incorrect. Because that would mean, so this is different from having like the entire function in absolute value. Right? In that case, you would just take any part where the y is negative and just like reflect it. But in the case where we have g of absolute value of x, what happens is that we keep the graph the same for, so the graph stays the same for when x is greater than 0. But when x is less than 0, we put in the y value for the positive counterpart. Right? So let's say we had this value of x. Right? So for this value of x, it's negative. So you would actually flip this to the right, get the positive value of y, right? Or get the y value for the positive version of x and just reflect it there. So to verbally describe this one, we would say it's actually, for x is greater than 0, we would keep g of x the same. But for x is less than 0, right? Then we would draw so we would reflect the g of x across the y-axis, right? So we would kind of keep this part and reflect it across the y-axis from the positive region, right? So we would reflect g of x where x is greater than or equal to 0, and we would reflect that across the y-axis. So if you want to find when this is less than or equal to 0, we would first work with this part, right? So we don't need to look at this one, the left side, because that's going to go away. So we just look for this 0 here. So the 0 here, we have like 1 and 3. So we get so when x is 2.5, right, it seems that, yeah, so when x is 2.5 and y is 0, right, that's our 0 point here. So for g being greater than or equal to 0, we would first have x has to be greater than or equal to 2.5. Okay, and then the left side would be a mirror reflection, right? So we'd have the same graph that goes like that, where this would be negative 2.5. So we also want x to be less than or equal to negative 2.5. Right? Only then will our g of absolute value of x be greater than 0. Right? So that's how you would do number 8. And let me just redo this problem for you while using the absolute value sign. Okay, so I'm just going to turn off our original function. And I'm going to show you the expression for x bar, or x absolute value. Okay. So g of absolute value of x means instead of 2x minus 5, we have 2 times absolute value of x minus 5. The whole thing is going to be divided by x squared minus 3. So actually, you don't have to put a absolute value sign if you're going to square it anyway, but I'm just going to do it. Okay? So you have absolute value of x, we're going to square that, and then we're going to subtract a 3 from that. Okay, so what happens there should be exactly what I showed you, right? So the right side is the same as our original one, but the left side is a mirror reflection of the right side, right? So for negative values of x, you would put in the same y values you would retrieve for the positive versions of x, right? So in this case, this function, g of x, or g of absolute value of x, is greater than 0 when x is less than negative 2.5 or when x is greater than 2.5, okay, or equal to. So that's how you would do number 8. I would say a lot of students would have missed this because they're okay plotting these functions, but they're unfamiliar with using like absolute value signs. So don't rely on your calculator to just plot all the functions for you. This is where your intuition matters, right? You need to have a intuitive understanding of what absolute values do to a function, okay, or to the graph. Okay, so that was number 8. Let's move on to number 9. We have a set of positive integers, 1 through 30, and Raghu randomly selects 3 positive integers from S without replacement, so we can only choose like one number. So each number can be chosen once at most, and then we're going to add them so that, and then we're going to check if the sum is divisible by 3. Okay, so the order is not important. So there's technically like 6 ways to choose 3 numbers, because if you have like 1, 2, 3, they could be rearranged in like 6 separate orders, but we're just going to treat that as the same selection. So the total number of ways in which we can choose these numbers would be like 30 choose 30. Right? But out of that, we want the case where the sum is divisible by 3. So let's think about what we want if the sum has to be divisible by 3. So if you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, one way we could choose a sum that's divisible by 3 is if you were to like add 3 consecutive numbers together, right? Like 1, 2, 3, 2, 3, 4, 3, 4, 5. That would be like perfectly fine. Because what happens is, like, if we have a number that's divisible by 3, like 3n, then this one would be like 3n minus 1, and then this one would be 3n plus 1, right? So as long as we have like 3 consecutive numbers, we're good to go, right? Or we could even think of it as if you have 3n, we have 3n minus 1, and we could have like 3n minus 2. So pick any 3 consecutive numbers, and I think you're good, right? But we don't have to stop there, because we could pick 2, 3, and the next runner-up is like either 1 or 4, but we could even choose like 7 or 10 or 13, right? Yeah, so there's like a number of options where we would choose, so it's not actually choosing 3 consecutive numbers, it's actually choosing a number from each of the third pairs, right? So what I mean by that is, if you have 30 numbers, we could say we have 3 groups, right? So the first group would be like 1, 4, 7, 10, right? So let's call that group, so if you have numbers from 1 through 30, let's say the first group is going to be 1, 4, 7, 10, all the way until maybe 28. So let's call that group 3n minus 2. Okay, so for n equals 1 through 10, we have 30 numbers. The first group is 3n minus 2. The second group, I'll say, is 3n minus 1, right? So that would be like 2, 5, 8, 11, 14, etc. The third group is going to be just 3n, like 3, 6, 9, 12. So if you choose one number from each of these, right, either like 1, 2, and 3, or 1, 2, and 9, or 7, 5, and 12, right, then that's going to give you a number that's divisible by 3. Okay, and is that the only way? Well, we'll have to see. So the first case is we have 3 groups of 10 numbers, right? And we might choose 1 from each group. So from 10 choices, we have 1. From the second batch of 10 numbers, we choose 1. And from the second batch of 10 numbers, we also choose 1. So this would be 10 times 10 times 10, which is like 1,000 ways in which this could happen. Okay. Now, it's also possible to choose a batch like 3, 6, 9, right? So if you choose numbers from the set that are 3 apart, or if you choose like 2, 5, 8, or 1, 4, 7, we know that's also divisible by 3, right? Because if we add like 3n minus 2 and another 3n minus 2, like this minus 2 is multiplied by 3, so it kind of cancels out, right? So we could choose 3 numbers from the first group, or 3 numbers from the second group, or 3 numbers from the third group. So actually, there could be 10, choose 3. So this would mean choose like 3 numbers from the same group, right? Where the group is 3n minus 2, 3n minus 1, or 3n. But there's 3 groups to do that. So we have 10 choose 3 times 3. Okay. So from one set of numbers that are spaced by 3, right? We choose 3 from that exact same group. So 10 choose 3, let's see what that is. 10 choose 3, that's going to be 10 choose 3, that's like 120. So this would be 3 times 120, or 360 ways. So net total, we would get 1,360 ways, for which we would get a sum that's divisible by 3. So as with like proof by contradiction, proof by induction problems, or just these like proof questions, I think it's kind of like a hit or miss. So it definitely is, I wouldn't say it's easy. Like sometimes you might get lucky, or sometimes you might just like see a straightforward approach. But if you don't see that right away, chances are you might just be like running down the rabbit hole on loose ends. So strategy-wise, like I would say, if it doesn't click with you, you could just like leave it. I mean, it's 5 points. It's not going to be the end of the world. Like there may be questions where you can put in the effort for like raw calculations or like graphing where you can make progress. So you might want to focus on those first and then come back to this one later, because this is one of the questions where like you might spend a lot of time and effort into this, but once you get that proof, you get all points. But if you fall short of it, it goes away. So it's kind of like a gamble, right? It's like high risk, high return problem. So for number 9, for these like proof questions, like I would try to be cautious about how much time I'm spending on this. Of course, the best thing is to just solve a lot of these kinds of problems. Like they are in your past paper question bank, so you could do that. But if you see a problem on combinatorics and you can't see like a way where you can, set up this problem-solving logic, then I would just skip to the next question. Okay, now let's move on to numbers 10, 11, and 12. So these are the more long response questions. We have like a lengthy scenario where we have a lot of sub-problems for this. Okay, so for these ones, it's especially important that you keep all your work organized. That's why the IB gives you separate solution sheets, separate pieces where you can write your answers, because you don't want to be all over the place going back and forth. You kind of want to keep track of all your progress. Okay, so let's first look at number 10. We have a weight that's suspended on a spring, and the idea is that it's going to go up and down sinusoidally. So the height is a function of time. Okay, so it's going to be time on the x-axis, height on the y-axis. And since it's a cosine function with no value of shifting for t, when t is 0, right, cosine of 0 is going to be 1. So we're going to get a here. So we would start off like at either the maximum point like that or at the minimum point like that. Okay, so that's something to keep in mind. And t goes from 0 to 10 seconds, right? So, and chances are, like, depending on the actual amplitude, a would have to change. And I would feel like the whole thing is shifted upwards. So there's no like negative height. It's all positive. So that's something to keep in mind. But let's just do it from part A. So what's the period of the function? So a typical cosine function, if we had like cosine t, it would go like 1 cycle up and down, right? It would start from the top, hit the bottom, come back to the top in 2 pi seconds, right? In 2 pi, like that's a period. But if you have 7.8 multiplied inside, that's like multiplying 7.8 inside this function. So this represents a compression, like a horizontal compression by a factor of 1 over 7.8. So this would actually be a pretty squished function where the period is 2 pi divided by 7.8. So that's like background knowledge. In terms of showing your work, you would just say the period is found by 2 pi over b, right, or 7.8. So that would be 2 times pi divided by 7.8. So 0.805 or 806 seconds. So for every 0.806 seconds, we would see this height kind of cycling from like minimum to the next minimum or maximum to the next maximum. Okay. So that's part A. And let's go to part B. So we're now finding the values of A and B, right? So for this A times cosine of 7.8 t plus B, so we probably established that, yeah, so this time the cosine function starts from the minimum. So by the time it returns to the minimum, this would be like 0.805 seconds. Right? So that's what we already established. But then let's also look at the weight. So it goes from 1 meter to 1.8 meters. So the amplitude is going to be 0.4 meters up and 0.4 meters down, right? So amplitude is a maximum displacement. So we know that the typical cosine function, right, it fluctuates from like 1 to -1. But since we're only fluctuating from 0.4 to -0.4, we would say A would be 0.4. Okay. But we also know that if you have a typical cosine function, it would start from the maximum like that. And here we have it starting from the minimum. So we could either shift this by a half. We could shift it by half a period, like 0.4 seconds. But if that's not an option, we would simply multiply a negative. So in this case, A would be negative 0.4. And what about B? Okay, so if you had negative 0.4 cosine, we would have something going from 0.4 to negative 0.4. But this whole thing is shifted upwards, right? So the 0.4 is shifted up to 1.8. The negative 0.4 is shifted up to 1. So the shift would be 1.4, right? So we have B is going to be plus 1.4. A is going to be negative 0.4. Okay. So as long as you have some understanding of how trig functions are transformed or how they work, you should be fine. And before moving on, let's enter that into our calculator, just so we can use it for our next steps. So we have negative 0.4 times cosine of 7.8x plus 1.4. We want to work with radians because, like I said before, we're not dealing with angles explicitly. We go from 0, so t goes from 0 until 10 seconds. Right? So considering that the period is like 0.8 seconds, we know there's going to be like at least 11 or 12, right? Somewhere around 12 full cycles in there. Okay, and we know our height goes from 0 to 2. So we don't need to see the full scale graph. Like this should be a sufficient range. Okay, so this is the graph that we see exactly as is shown on the paper. Now let's go to C. So how many times does a weight reach its maximum height in the first 5 seconds of motion? So if you look at the graph, we start from the negative part, and in one cycle, we know there's like 1 right here. Okay, so since this would be 0.805 seconds, or 806 seconds, we just need to look at how many cases we would have for x equals 5, right? So if you have t and height, up until t becomes 5, we have around 1, 2, 3, 4, 5, and around 6 different oscillations that go like that. Okay. So actually the best way to do it is by just figuring out 5 divided by 0.806. So we know we can fit in around 6.2 of these, right? So we have like 6 full cycles here, and then it would kind of continue, but we'd cut off there. So we actually have 6 maximum points and 6 minimum points. Or actually 7 minimum points. But as far as this question goes, we know there's 6 points where the maximum is reached. So 6 times the max height is reached. Right, so on your graph, you would say it's, so let's go from 0 to 11. So if you look at from 0 to 5, we would see that there is 1, 2, 3, 4, 5, 6, right? And then it kind of cuts off from there. So you can check that out visually. Okay. Or you might show how you're dividing 5 by 0.806. So it's like 6 point something. So there's around, for t between 0 and 5, we know there's 6 maximum points. Okay. And then let's look for the case where the base reaches a height of 1.5. So for our graph, we're trying to set a height of 1.5, where the graph kind of goes like that. And we want to look for this point, because this is when the height first reaches 1.5. Okay. So what we would do is we could just find the second graph as 1.5. Right. And then we want to look for the intersection. So it goes from 0 to 0.5. So we see that our intersection happens at t equals 0.23378 or 234. Okay, so when t is 0.234 seconds, the height is 1.5 meters, and that's like the first case where the base is reached. Yeah, so we solve for h of t is 1.5. We know there's multiple solutions because cosine and sine are periodic. They repeat every cycle. But the very first one we see is 0.234 seconds. Okay, so that was pretty straightforward. Part E. So we're taking photos of the weight at different points during the first 5 seconds. Okay, so we still want to plot out the first 5-second oscillations here. Okay, so yeah, it's exactly what we see here. So we would see like starting from 1, we have 1, 2, 3, 4, 5, 6, and then you go a little bit here. So this would be like 5. So the 6th cycle would complete around 4.8 seconds-ish. So if we were to take a photo at any point, and if you want to find like the times when, or the probability where this is greater than 1.5, what we want to do is we want to draw the baseline at 1.5, and we want to find the regions of time, or the intervals of time, where this graph was greater than 1.5, right? So if there's an equal likelihood of pressing the shutter on the camera, right, so then the probability would correspond to the total amount of time, right? The time would be equal to the probability. Probability of height being a certain value. So if we just look at one full cycle, right, we could find the case where this is like 0.234 seconds. And the second intersection, if you were to look for it, oops. So we have 0.25, and maybe we'll do like 1. So we have the second one at around 0.572. Right? So if you were to look at one of these, right, it would be 0.572 minus 0.234. So that's like 0.338 seconds. So in one interval in one full swing, there's like 0.338 seconds for which the period is above this height. So if you take your photo at that instant, then you would get the weight being greater than that height. And throughout the whole 5 seconds, right, there's not just one of these instances, but there's actually 6 of these instances. Right? So we want to multiply that by 6. So throughout around 2.028 seconds, right, for a total of 2.028 seconds out of 5 seconds, right, the height exceeds 1.5 meters. So 2.028 divided by 5, that would give you 0.4056. Right? So the probability is going to be around 0.406. Okay, so that's going to be your probability. Okay. All right. Yeah, so this is during the first 5 seconds, not the first 10 seconds. So yeah, that is correct. Okay, so now let's do number 11. This is pretty lengthy, combining combinatorics and probability. I would rate this somewhat difficult because even though, so you would even use maybe like normal, so you don't have to use like normal distribution or binomial distribution as we've done earlier, but it's kind of important to understand how you can deduce probabilities from a given situation, right? So this is pretty high up there, and if you kind of miss the first few questions, like it might lead to you not being able to solve like the following ones, because here you have to understand like independence between events, and these events are happening like sequentially. So actually, what we have is non-independent or dependent events, because if you have drawing balls or tickets, raffles without replacement, then the result of the first outcome affects the ensuing probability of the following outcome. So yeah, like this is something where a simple formula doesn't just like bring you a clean, easy solution. You might have to work your head around how this works. So it would be kind of like number 8, that vector question, with you thinking about how these vectors would interact. In this one, you'd have to visualize like how these balls and in the system, like what they're doing, right? Or what's happening to the system once a certain action is taken, okay? So you kind of need to understand the full story behind this problem, is what I'm trying to say. So let's dive straight in. So there's a game of chance involving 2 balls, right? Drawing 2 balls out of a random box without replacement. Okay, so this is important because if there's like 7 out of 10 yellow balls, right? On the first, second, third draw, if you're keeping on replacing them, the probability is fixed. But if you're not replacing them, right, we have to subtract like the ball taken from the previous draw, right? So let's say we have R red balls and Y yellow balls, and we say that PYY, right, is the probability of drawing 2 yellow balls from the box without replacement. So this would mean we're drawing, so it could represent 2 things. Like if you're more of a visual person, you might draw something like yellow on the first draw, red on the first draw. And then for the second draw, you get either yellow or red, right? Or then you could get red, then yellow, or red, then red. So you want to find the probability where we get yellow, then yellow again, right? So in the first one, you would say that there's a y over r plus y chance that you get a yellow draw, or r over r plus y chance that you get a red draw. Okay, and then the catch here is that the probability changes depending on the outcome. Okay, so what I would like to say is probability of yy is probability of getting y on the first draw, or I'll say something like probability of getting a yellow on the first draw. And then you multiply probability of yellow on the second draw. But the probability of yellow on the second draw depends on what you chose for the first draw. So given that we chose yellow on the first draw, right? So this is the expression that we want. And what I mean by that is, getting yellow on the first draw is nothing more than y over y plus r. Now, if we chose a yellow ball already, then the remaining balls would be, so this would be like 1 y plus r minus 1. And then the remaining yellow balls would be y minus 1. In the case of drawing a red one, there's still red balls here. So r red balls here. So there's y minus 1 yellow balls, r red balls. And the total would be y plus r minus 1. Okay, so this is a conditional probability. So you have to multiply. There's one less yellow ball, right, and a total of one less in the total pool. So you have to multiply these two, right, to get the total probability of drawing 2 consecutive yellow balls without replacement. And the question says this should equal 1 over 3. Right? So if you set that up, that's pretty much like 70–80% of the problem. Because in order to get the expression here, all you got to do is just simplify this, right, and do some algebra to get this end result. So let's try that. Let's see. So what we would do is, in the denominator, we could do like y plus r times y plus r minus 1. So notice I kind of grouped the y plus r together because that might come in handy instead of expanding everything. And then I have y times y minus 1. That's going to be equal to 1 over 3. Okay, so I'm going to do cross multiplication. I'm going to multiply 3 to both sides and y plus r times y plus r minus 1 to the both sides of this equation. So the end result is going to be, I'm going to write this at the top. I get 3y times y minus 1 equals y plus r times y plus r minus 1. So that's going to be y plus r squared minus y plus r. Right? So if we simplify that, we should get the end result here. So I'm going to do 3y squared minus 3y. And then I'm going to get that equals, or I'm going to move everything to one side anyway. So I'm going to do like, so this is going to be y squared plus 2ry minus r squared. So I'm going to subtract all that. So you can kind of take your own time to work out the algebra. And then I'm going to add y plus r. That should equal to 0. And simplifying everything, I get 2y squared, right? Because this and this cancels out. So I get 2y squared. I get y and minus 3y, so I get negative 2y. And then I get negative 2ry. So I can group that as negative 2 times r plus 1y, right? Because I have negative 2ry and negative 2y. So I just kind of skipped that, did that algebra in my head. So that goes away. And then I have r squared. So r minus r squared. So I'll just write that here. So this is exactly what the question was asking for, right? So when you see us show that problem, don't try to tackle this formula right away, because if you try to manipulate this and show that it's the result of, like, so if you try to do this the opposite way, you're not going to go anywhere. Try to pretend you don't know this result and just explain how you would set up the formula for this probability. Okay, and then algebra will hopefully take care of the rest, right? And even if it doesn't work, hopefully you might get a point or two for showing your line of logic or how you're tackling this problem. Okay, so we have this expression in A, and by solving that same equation, we want to show that y is equal to this thing right here. So I have 2 times y squared minus 2 times r plus 1 times y plus r minus r squared equals 0. So this is actually nothing more than using the quadratic equation. So remember how if you had like ax squared plus bx plus c equals 0, then x can be found by using the coefficients like negative b plus minus square root of b squared minus 4ac over 2a. Right? So in this case, we have y instead of x. So it's a quadratic equation using y. So we're trying to find the root of y. And in the coefficients, we happen to have r. Is that okay? Yes, because r is an unknown value, but it's a constant. It's not a variable. So we can just set that up. So A is going to be 2, B is going to be negative 2 times r plus 1, and C is going to be r minus r squared, right? So using that, let's just set up our quadratic formula. So y is going to be negative b, or it would be negative of negative 2, so it would be 2 times r plus 1. Okay. Plus minus square root of b squared, so that would be 4 times r plus 1 squared, right? So I get 4 times r plus 1 squared, and then I have minus 4ac, so I have minus 4 times 2, so that's like negative 8. And then I have c, so I have negative 8 and r minus r squared. Okay, all over 2 times a, where a is 2, so that would be 4. So now I'm going to simplify this once more. So on the left side, I would just get r plus 1 over 2, which is promising, right? We just got to get the rest result here. And I'm going to do like plus minus square root. So I'm going to leave the 4 and I'm going to simplify. So I get r plus 1 squared. So mentally doing that, I get like 4r squared plus 2r. So it's like 8r plus 4. And then I would do minus 8r, minus 8 times minus r squared, so it's like plus 8r squared. Okay, so I know that algebra is a bit challenging, bear with me, but you could just take the time to write everything out and you'll get the same thing as me. So we get r plus 1 over 2 plus minus the 8r would go away, right? And then we can kind of factor out the 2. So we have 2 square root of r squared, or actually, so we would get 12r squared plus 4. But if we factor out the 2, we get 3r squared. And then plus 1, right? All over 4. So we would get r plus 1 plus minus square root of r squared plus 1 over 2. So it seems like we're almost there, but we don't have the negative sign, right? So it gives, there's probably a condition that makes it so that the minus sign doesn't work, right? So why would that be the case? So chances are, so y stands for the number of yellow balls. So we don't know what the minimum value of y might be, but if we actually subtract this, chances are square root of 3r squared plus 1 is definitely going to be greater than r plus 1, right? So we don't want a case where y is negative. So that's why y has to be r plus 1 plus square root of 3r squared plus 1 all over 2, right? Because y has to be greater than 0, r has to be greater than 0. You could actually check this by solving for y in terms of r. Okay, so I mean, we do have to put this in the calculator anyway because we do have to find the pairs of r and y. So let's see what happens if you had the negative version. Okay, so in our case, x is going to be r and y is going to stay the same. So let's say y1 is x plus 1 plus square root of 3x squared plus 1. And let's say that divides by 2. So the whole thing is going to be divided by 2. Okay, so that seems quite all right because r would be a positive number. So we could have r going all the way up to 20 number of red balls, and then we could show yellow balls like y going from maybe -2 all the way to 20 as well. So in this case, if you were to show the red balls as a function of the yellow balls, I think it's okay if we have this expression. But the moment we had a negative there, right, if we were to have considered the negative, chances are, yeah, you'll see that if we have the negative version, as the number of red balls increases, y would go to a negative part. Okay, so yeah, so that's why we disregard the negative sign, because there's so many cases where square root of 3r² plus 1 is going to be greater than r plus 1, making this whole thing negative. Okay, so for part B, that's the justification for taking out the minus sign. And for part C, we can just find two values of r and y. I mean, there's only going to be two values for which this is going to be an integer. Okay, so we're still solving the same equation from part A, but the catch is they have to be integers. So it's the same graph, but they have to be integers. So let's see. So you could actually go to the table. So if you click like second window, you can start from like the table. So you could say, I'm going to start from 0. Right? So I'm going to start from there being 0 yellow balls. And I'm going to get the corresponding y values for each of these red ones. So I go to second table. So if I start from r is 0, I get y is 1. Okay. So that means there's just like, one yellow ball, but then that wouldn't make sense, right? Because then after you draw one ball, that kind of goes away. So the calculator function you need to use is like second table set. So if you click second window, that allows you to start from like r equals 0, and we can keep on doing like a +1, and then that would show you the corresponding y values. And then you would go to second graph, which would show you the table values, right? So if r is 0, y is 1, but thankfully we have r is 1, y is 2, right? So if you have one red ball and two yellow balls, then the chance of getting two yellow balls is going to be like 2 over 3 times 1 over 2. So that's 1 over 3. So that's correct. And then if you keep on scrolling, we have r is 4, y is 6. Okay. So there we go. We found our two solutions, right? So that should be enough, but just to be safe, you want to do a mental exercise in your head. Like if there's 4 out of 10 that are red, then the first draw, we're going to get like 6 out of 10, then we get 5 out of 9, right? Because we already drew one yellow ball. Then that's going to give us a net probability of 30 over 90, which is indeed 1 over 3. Okay. So that allows us to find the case where probability of yellow and yellow is 1 over 3. Now let's do part D. We're considering a game where now we have 3 balls out of a box and we don't have any replacements. And we have 10 red balls and y yellow balls, and we're trying to do 3 yellow balls consecutively. Okay, so let's try to write what PYYY is. So this one would be you're drawing a yellow ball out of the first batch where there's like 10 plus y balls. Then we multiply the next case. So if we already drew one yellow ball, then there's y minus 1 yellow balls remaining. And then there's 9 plus y total marbles, or total balls remaining. And then we have y minus 2 over 8 plus y. So in terms of y, I guess the simplest we can go is y times y minus 1 times y minus 2 over y plus 8 times y plus 9 times y plus 10. Okay, so I don't think you have to go as far as to simplifying this even further, because it's pretty much impossible to get it any simpler than that, right? E. So based on that, we now have a yellow ball that's added. So there's like 10 red balls and y plus 1 yellow balls. So the probability of drawing 3 yellow balls from this box, so again we have the same PYYY, right? But it's different. But now it's that's going to be twice the probability from earlier. So if you recall, the earlier probability was y times y minus 1 times y minus 2 over y plus 8 times y plus 9 times y plus 10. So this was the probability expressed in part D, but we have double that. So twice that is equal to this new case. So drawing 3 yellow balls from this box without replacement. So we would actually have y plus 11 balls total and y plus 1 yellow balls. And then we get y yellow balls remaining after the first draw with y plus 10 remaining, and then y minus 1 over y plus 9. So both of them are probabilities where we get 3 yellow balls, but the left probability is twice that of the right one. And we just need to find y. Right? So it just boils down to an algebra problem. But before bringing out your calculator, let's see how we can simplify this. So we can cancel out the y minus 1, y plus 9, y plus 10. So that's just 2 times y minus 2 over y plus 8 is y plus 1 over y plus 11. Okay, and if we were to use algebra again, we could cross multiply. So we get y plus 1 times y plus 8. That equals 2y minus 4 times y plus 11. And let me take this to the top. Y squared plus 9y plus 8. That's going to equal 2y squared minus 4y plus 22. So plus 18y minus 44. I'm going to simplify everything by moving to the right. So I get y squared plus 9y minus 52 is 0. Right? So we're almost there. What multiplies to negative 52 and add up to 9? I can think of 13 and 4, right? So if we have y plus 13 times y minus 4, then we get y squared, negative 52, and we get 13y and negative 4y. So that is indeed 9y here. So y has to be either negative 13 or 4. So that means the initial number of yellow balls in the box would be 4 yellow balls. Okay, so it kind of keeps on testing your ability to comprehend the situation, like the different conditions of independence or replacing versus not replacing. And it kind of, I think this kind of tests your algebraic skills to the limit. So always be clear to, do the best practice of, like simplifying before multiplying. If you have like a lengthy expression, we want to keep everything on like the same line without us writing all over the place, and make sure you have legible handwriting, not necessarily for the examiner, but for your own sake, right? It's painful to watch students, be unable to recognize their own work, so they have to like redo the solution. So those hard skills will come into play in getting all points for number 11, right? So it is pretty lengthy. It kind of does test your stamina, but if you stick to the basics, you should be able to stick through with this question. All right, so let's now do our final question where we have differential equations, and there are many ways to solve a differential equation. Separation of variables, integrating factor method, Maclaurin series, and Euler's method. So this question kind of touches on all that, including substitution. So it even makes you do a Euler's method calculation, and then also it makes you kind of solve it manually with like substitution techniques, and then it kind of asks you to think about why we may get similar or different results. Okay, so the first one is a Euler's method problem. So there's only one step we need to do. So we would start from x is 1 and y is 2. And with that, we can find our dy over dx value using this expression. So since there's only one step, you don't need to really use your calculator as much. But in case you need to do like 3, 4, or even 5, 6 steps, we would use the store function, right? Store as variable function on our calculator. So that would come in really handy. So let's see what that means. So normally what you would do is, in order to go from x to the next one, we would simply add the step size of 0.1. And then as for y, what we do is we calculate our dy over dx based on these x and y values, right? So we'd have 1 squared plus 3 times 2 squared all over x times y, so that would be something like 1 times 2, right? So that would give us something like 13 over 2, so that's like 1.3, right? So we get 4, 12, 13, so we actually get like 6.5. So we actually get this y value by doing y plus 0.1 times 6.5, right? So we can do this in one step, so it would just give us 2.65 right away. But if you were to use your calculator, this is what you do. You would first store the 1 value as x and 2 value as y. So from this point onwards, whenever you enter a x or a y, you get 1 and 2. Next, you would find the expression. So we take our original value of y, we add 0.1 times the slope, right? So the instantaneous slope with the current x and y value can be found by x squared plus 3y squared over xy. Now this is going to replace our y value, right? So we would update our y value, and we would also update our x value by simply adding 0.1 there. Okay, so then the calculations would be done automatically, and the advantage of this is you can use it over and over again for multiple steps. So if you click on the STO button on this calculator, you should be able to store numbers. So you could store 1 as x, and you could store 2 as y. Okay, so let me use the alphabet y. So every time I call upon, say like x, I'm going to get like x squared. That would just do like 1 squared. Okay, x plus y would simply give me 3, right? So my x and y values have variables. They have a value stored with them. But now what I'm going to do is I'm going to take my y. Okay, so I have my y, but I'm going to add 0.1 times the slope, right? So it's x squared plus y squared plus y squared. And then I'm going to divide that by x times y. Okay. And then I'm going to say that's going to update my new value of y. Okay. So my new value of y would be updated as follows. Oh, it actually is, okay, so we'd have to try again. So my value of y is 2, and I would say it's x squared plus 3y squared, right? Right, so my new value is, in decimals, indeed 2.65. Right, and then for the next step, I would do update my x value. So I would take x plus 0.1. That's going to be stored as my new value of x, right? So then I would get 1.1. So if I want to do this once more, I would do, okay, based on this new x and y value, let's get the next y, which is 3.4. And then let's get my next x, which is like 1.2. So this using store method is pretty handy when we do Euler's method, especially for other cases where we have to do like multiple processes like this. Okay. Next, let's do part B, but this time it just sends us on a journey where you have to solve this by hand. Okay, so we want to solve the differential equation. So the differential equation was dy over dx equals x squared. So it was x squared plus 3y squared over xy. And from this, we want to get y is x times square root of 9x to the power 4 minus 1. Okay. So this is like a completely separate track from what we did in part A, because we have to do this manually. So it seems like we might benefit from using a substitution. Because if we just do this mentally, we know we get like x over y plus 3y over x. So we could try doing something like v is y over x, right? So this substitution kind of helps. So let's actually try setting y is equal to v times x. Okay? Because we have a y over x or x over y relationship in there somewhere, we know this is going to help us. So dy over dx is going to be, in that case, so we'll leave x as is, and y is going to be 3v squared x squared over, we get vx squared. Okay. And if we were to differentiate y with respect to x, we would get product rule. So we get v prime x plus x prime v, or v prime would be dv over dx times x plus x times x prime times v. So it would just be this one. Okay, so this is our substitution that we need to put in. So dy over dx would be dv over dx times x plus v. That equals x squared plus 3v squared x squared over vx squared. Okay. And then we want to simplify so that we can separate everything, get all the variables in one place. So let's multiply vx squared, right? So the goal is to get x's on the one side and the v's on the one side. Okay. So let's put in vx squared, multiply that to all sides. So you get v squared x squared times dv over dx plus v squared x squared is equal to x squared plus 3v squared x squared. Okay. And then we could try simplifying further by dividing by x squared, right? So if we divide the x squareds out of it, we would get a x cubed here. So this would be an x cubed. So the only x we would have is, okay, so this would be v squared x cubed, right? So if you divide away the x squareds, we would get v squared x. Actually, this would just be v minus. So it would be vx cubed, right? So we would get vx times dv over dx plus v squared. That equals 1 plus 3v squared. Okay. So that's what we get. We could subtract the v squared. So we're going to get vx times dv over dx is equal to 1 plus 2v squared. Okay. Then further simplifying, we could get v over 1 plus 2v squared dv on the left side. On the right side, we get 1 over x dx. And now we have a basis to do separation of variables. So we can just integrate both sides, and this is where we would kick off part 2. Okay, so this would be like part 1. And part 2 would involve trying to work this out. Okay. So if we have 1 plus 2v squared in the denominator, we could try and substitute that out. So what if we say u is 1 plus 2v squared? Then du over dv would simply be 4v, right, if we differentiate with respect to v. And then we could say something like dv is going to be du over 4. Okay. So we can then substitute this as integrate. Okay. So we get v. Okay, so we get v dv is d over 4. So we could get integrate u goes in the denominator, and instead of v dv, we would get 1 over 4 du. Okay. So we get 1 over u, right, and du. So that's what we get on the left side. On the right side, we would just get integral of 1 over x dx. Okay. So we would just get a bunch of natural logs. So we get 1 over 4 ln u is equal to ln x plus c. Right, some integration constant there. Okay, and now we want to change it back to the v's again. So 1 over 4 ln 1 plus 2v squared is ln x plus c. Okay, and how do you find c? Well, if you go to the earlier question, it says when x is 1, y is 2, right? So we have x is 1, y is 2. Since y is v times x, v would just be then 2 as well, right? So if we were to substitute that in, we could get 1 over 4 times ln 9, because v is 2. That equals ln 1 plus c. But ln 1 is 0, so we get just c. So now we kick off the third phase. Right? So we know what our c is. So we now write our expression as 1 over 4 ln of 1 plus 2v squared equals ln x plus 1 over 4 times ln 9, okay? Now, we could just multiply 4 to both sides of the equation. So we get ln of 1 plus 2v squared is equal to 4 ln x plus ln 9, okay? And the 4 could go as a power, right? So we get 1 plus v would be y over x. So we'll just get y squared over x squared, or 2y squared over x squared. That equals ln of 9 times x to the power 4, right? Because if you have natural logs, we can just merge it all together. So the contents inside the natural logs are going to be equal to one another. So that means 1 plus 2y squared over x squared is equal to 9x to the power 4. We subtract 1 on both sides and multiply by x squared. So 2y squared is going to be 9x to the power 4 minus 1 multiplied by x squared. Okay. So we divide by 2, take the square root. So y would be plus minus x square root. So we divide by 2 there. So it's 9x to the power 4 minus 1 over 2. So that should be the correct answer, right? Because there's also the negative part. But we know that x and y must both be greater than 0. So we exclude the case where there's a negative. So it should be y is x root 9x to the power 4 minus 1 all over 2. So for those of you who can't see, it's pretty much the same thing, right? So we get the same solution as required by our answer. Okay, so we want to show that this is the case. So our end result is indeed this one, because we don't look for negative values of y. Okay, so that was a pretty lengthy one. I would say there are 3 distinct phases. First one, recognizing the substitution of y equals v times x. Second one, there's a new substitution where we have integration by substitution techniques. Like, so we have a new variable like u instead of v. And then the third one would be just setting the logarithmic exponential equations equal and just using algebra, right? So it would be logarithms and exponents. So that is a lot of points for part B. I would definitely consider that one of the more challenging ones, and you would definitely need to allocate a lot of time to this problem. So now let's look at part C. So when x is 1.1, remember earlier we said with Euler's method it was 2.65, right? So the approximation in part A was 2.65, right? When x was 1.1, y was 2.65. But we can find this again using y is x square root 9x to the power 4 minus 1 over 2. So it's 1.1 square root 9 times 1.1 to the power 4 minus 1 over 2. So simply, even if you miss the part in B, you could just plug this in to get a free point. So 1.1 times square root of 9 times 1.1 to the power of 4 minus 1. And then we divide this whole thing by 2. So it gives us like 2.71422 or 2.71-ish. So our value is slightly higher than what we found in A. And that has to do with the concavity of this, right? So imagine, okay, so if you look at dy over dx, okay, so if you look at the graph of dy over dx, remember that it was x squared plus 3y squared over xy, right? So if we were to look at d squared y over dx squared, so if you were to differentiate that once more, then we would recognize that it's all just positive. So it would be concave up. So if you were to just do, okay, so what we could do is, okay, so actually we can just substitute in x is 1 and y is 2. Okay, so for this value of x that's between here, what's gonna be true is that, so actually you can just look at y is x. So we would start from like y is x square root of 9x to the power 4 minus 1 over 2. So if you do that, you will find some interesting results. So if you have x square root of 9x to the power of 4 minus 1 over 2, right? And if we plot this for x is around 0.8 to 1.3, right? Because we want x's from 1 to 1.1, right? So 0.8 to 1.3 maybe. And if we do like 2. So if you kind of zoom out, we notice that the graph itself is kind of like that. So if you have x versus y, it's a concave up function, where the d squared y over dx squared, or the secondary differential, is greater than 0. So what do we mean by concave up? What we did with Euler's method was when x was 1 and y was 2, we found the instantaneous slope at this point. And then we assumed what would happen if we go by a step length of 0.1, in which case we would have an estimate of y, right? So we'd have an y estimate. But the actual value of y is likely going to be greater than this one, right? Because this is only an estimate of a concave up function. Right? The actual y value may be much higher than that. Right? So we see that the Euler's method would underestimate for concave up functions. Right? So for concave up, we see Euler's method underestimates. And we would say the same is true for concave down. Right? So concave down, Euler's method would overestimate. Okay? So that's the insight the question wants you to have in part D. And then let's do part E. So what we have here is we have a point of inflection at point P. So at d squared y over dx squared equals 0, that's where the inflection would happen. Or we could just plot dy over dx. Right? So we could just plot dy over dx and x. So dy over dx was simply x squared plus 3y squared over xy. So it's kind of hard to put this into the calculator, but the good news is we can substitute in this expression for y. So in your calculator, we would have y1 equals the expression for dy over dx, but in terms of x only. So we get x squared plus 3, and instead of y squared, we would get this full expression squared all over x times y, but instead of y, we have x square root 9x to the power 4 minus 1 over 2, like that. Okay. So if we put that equation in, we would get x squared plus 3 times x square root of 9x to the power 4. So this is a pretty lengthy equation, so you want to make sure you're keeping your parentheses in check. Right, so we close the parentheses here and do a squared, and then we close, and then we would divide by x times, so instead of x, we'd have x squared times square root of 9x to the power of 4 minus 1 over 2. So for those of you who are kind of lost, what I did was I basically plotted dy over dx in terms of x. Right? So I eliminated the need for using y because we can substitute the relationship from earlier. So if I were to graph that, I would get a graph that looks kind of like that. And this local minimum is of interest to me because the stationary point, or the tangent line, is has a slope of 0 in the dy over dx in the graph. That means d squared y over dx squared, or the secondary differentiation here, is going to be 0. Okay, so let me just look for that point, the minimum point, right away. So between 0 and 1.5, this would be x is 0.656. So at that point, our dy over dx is going to be 3.46. And our d squared y over dx squared because you notice that slope is decreasing then increasing, right? So it's momentarily 0. This is going to be 0, so that's our inflection point. So this is P. So we want to find the x coordinate of P. So that would simply be x is 0.656. All right, so we're on our final question. So we are given the secondary differentiation of y. So we have d squared y over dx squared. So doing this manually would have been tough, but thankfully we are spared from that dilemma. And we want to use this expression to show that point P lies on y equals mx. So basically, it's on a point where its x coordinate is x, y coordinate is mx, right? And we want to find what this m value would be. So on point P, we established earlier this is a inflection. So this would have to go to 0. So what we would do is we would take this expression like negative x to the power 4 plus x squared y squared plus xy to the power 4 over x squared y cubed. We would set that equal to 0. Okay. And since x and y are both greater than 0, we would do okay just multiplying, or actually we would do okay just dividing, or we would just, yeah, so we would just multiply x squared y cubed to both sides, because that would be a non-zero number, right? Multiplying 0 to both sides would be problematic, but if you were to multiply like x squared y cubed to both sides, that's okay. So we have negative x4 plus x squared y squared plus 6y to the power 4 is equal to 0. And if point P lies in the straight line where y equals mx, that means we can use y as mx from here on forth, right? So we get negative x to the power 4 plus m squared x squared for y squared. So it's m squared x to the power 4 plus 6m to the power 4 x to the power 4. That's going to equal 0. Okay. So that means we have x to the power 4 times 6m to the power 4 minus or plus m squared minus 1. That's going to be 0. And since x is greater than 0, it cannot be 0, right? So using null factor law, if the product of x to the power 4 and this expression is 0, then at least one of them, this one, has to be 0. So we're now solving for 6m to the power 4 plus m squared minus 1 equals 0. So we can factor this as 3m squared and 2m squared, right? And then we could do like plus 1 minus 1. So m squared actually would be minus 1 and plus 1. Okay. So we have 3m squared minus 1 times 2m squared plus 1 is equal to 0. So 2m squared plus 1 being equal to 0 means m is a complex number, so we can't really do that. But we can solve for 3m squared equals 1, right? Because then m would simply be plus minus 1 over root 3. Okay. And since we want x and y to be in the first quadrant, if m were to be negative, like x and y would be in the second and fourth quadrants. So m would have to be positive, right? So m has to be greater than 0, so m is 1 over root 3. So this because x is greater than 0 and y is greater than 0. So point P lies on y equals 1 over root 3x, because this expression for d squared y over dx squared goes to 0. So a recap of this problem, like this was the last and probably the longest heavily weighted calculus question. I think Euler's method is its own thing. So if you know how to use your calculator, or at least if you know how to set this up, you can do the Euler's method. But then the main challenge is getting the manual solution. So we call this the analytical solution. So the problem usually guides you through on what to do. Like it might ask you to separate the variables, or it might ask you to use a substitution in a certain format. But otherwise, you might be left alone at it. So if you figure this out, you're good to go. But if you miss this one, you're going to lose a lot of points, right? But that doesn't mean you can necessarily like lose the following points automatically, right? You can still salvage this because a key point in this question, in this type of question, is like making you compare the numerical versus analytical, right? It makes you compare the Euler's method versus the manual method, right? So you might get a hint or two and try and get a few of these like error carried forward points, because if you're just commenting on which is greater or why was it an underestimate or overestimate, you can just figure out the concavity of the graph. And then part E and F, yeah, so don't try to always draw like y versus x, right? Because you can also draw dy over dx, or we can even draw the second order differentiation versus x. So keep in mind that since we have our calculator, we have those options open. Okay. F was just making use of all the hints that were given so far. So if you just tried solving this expression right away, you would have been lost. But thankfully, we know, that point of inflection means d squared y over dx squared is equal to 0. So it kind of makes you look back at the past problems, the past hints. So you kind of have to see the bigger picture in solving this one. Okay, but I would definitely say you're not alone if you lose a few points in the last question, because it was indeed one of the more difficult level of questions. But thankfully, we're done with this paper. Thank you for watching.